good afternoon once again. I'm Oldrich Priklenk, and I am working on novel methods for quantum simulation and beyond. So, first off, something about me. In the high school, in the first years, I was focusing on philosophy, and I wrote a paper on the comparison of science and phenomena in a relationship to truth. In the end, I placed in the national round of scientific competition with it in Czech Republic, and the it led me to think about physical systems, and in particular the quantum ones. So that got me into working with Arctic and programming for experiments at ultra cold plasma laboratory in Prague. And currently I am deploying Arctic, which is advanced real-time infrastructure for quantum physics at Metrology of Time Laboratory, and I am developing a new user interface. So, uh, and of course, now I am part of CCIR summer course, where I am just about figuring out the research. So, just a quick disclaimer: I am still working on my research, so the stuff that I present here is not yet fully published or done. So that is the basis. And the objectives of my research are twofold. First, I want to analyze hydrogen atom using Dirac equation, Dirac, which the second one is try and simulate ion using density functional theory. This I want to simulate this calcium ion, as that is the main method we use in ion trapping for as the basis for qubits. So that's why I want to simulate it. And the third objective is explore novel approaches how to simulate particles. In particular, try to make some cohesive framework in Python or some programming language, so it does not need to be done all by hand, which is quite tedious. Something in the beginning, something quick about physics. So and how we got to quantum physics. So in classical systems, we exploit the power of variables, right? So it's quite basic, but the x and t axis form a line, and that represents all the points, all the possible points that the particle can move on. And the thing is that it's just a line. Whereas when we step into a wave-like behavior, then we introduce another axis, the imaginary axis. Unfortunately, the picture is not there, but we can write wave behavior using the Euler's identity, which introduces the imaginary axis, and that gives the particle much more space in which it can move. So it's not only bound to travel in one path, but it can travel like a wave, meaning it can move forward and backward in time and also move in space. And then we have another leap, which is the quantum, and quantum particles can have even more degree of freedom. So now the expressive power is that we add spin and have the different orbitals and wave functions, meaning that we represent all the possible paths the particle can take. It's more expressive. So that was just a quick physics overview. And now let's get to the Dirac. There are many approaches how to simulate a quantum particle. The most popular one for instance, the quantum chemistry is Schrödinger equation. However, Schrödinger equation is mm, the Dirac equation is more expressive because first it encodes spin intrinsically, and second, it accounts for special relativity, meaning uh, it also describes how the particle moves in space-time, where the Schrödinger model is more constant in this case. And of course, Dirac is basis for quantum electrodynamics, which was developed later. So we can transition there, and the QED then is part of other frameworks in physics like QFT. So that will be useful later on if you want to expand. Um, so this is the basis Dirac equation that we'll use. Um, and I wrote out the terms that are used in it. So as you can see, there is the space-time that is here. That is the first thing. That is partial derivative. Then we have the internal state of the particle, known as spinor, which in Schrödinger's picture is very similar to the wave function. Then we have the gamma matrices, which essentially connect with under Lorentz variations. I'm still studying, so but the gamma matrices connect the spinor and the spacetime together. So we have separate spacetime, and for each point in space and time, we have internal state. So and some states are forbidden by the symmetries, but essentially the particle can move. It can have a different state at every different point in space and time. So that gives quite a lot of possibilities and how the particle can move. That's why the quantum mechanics is so abstract and weird sometimes. Um, and then, of course, because we want to simulate hydrogen, then we add as an external electromagnetic potential the protons, which is the A term. Um, and what are the expected results of such a simulation? I would like to simulate hydrogen wave function as is described in this picture, the famous picture. So this shows us the density of the electron density and the clouds of the electron clouds around the hydrogen, which is analytical solution from Schrödinger equation. However, I would like to do the same with the Dirac, and I would like to map and see if the Dirac equation gives us the same results as the Schrödinger, with having more expressive power because we can define the fine structure states of the qubit. I don't know if I'm speaking to, yeah, so that's it. Regarding the DFT, essentially, big problem in quantum physics right now is that we that in making interactions with many particles, many electrons, is quite hard. It just exponentially gets larger. So we search for methods to simplify it, and that's where the electron density comes into play. Um, uh, and the DFT. So essentially, instead of finding the precise analytical solution for the particle or for the ion with, I don't know, let's say 20 electrons, we only search for the electron density, which can be expressed using this term here. So um, and yeah, and the way we do it is that mm, we essentially well, I will I actually I'm still figuring out the DFT because I've just learned it like 2 weeks ago in the in the CCIR summer course. So that will come. But essentially, we define just the potential, which is the VF term, and the kinetic term, which is the H bar divided by 2m times the term times the well the partial derivative for all the spatial dimensions, and uh, and we equate this to the wave function. So which is the right term in the equation, and as the potential includes all the interactions between the electrons, um, approximation. That means that we can essentially get the correct wave function just by knowing the potential and the kinetic energy, which simplifies the problem. Um, to know just the density and not the interactions between them. Um, what are my next steps in the research? I would like to now finish the model of the hydrogen atom, um, and find the wave functions for it using the direct equation. And I'd like to simulate the calcium ion using the DFT. And apart from that, I am also working on uh, on a quantum algorithm for a computer for a quantum computer, which we might implement, and I might test it out in during my internship at the UPT, as I talked about in the beginning, at the metrology laboratory. So maybe I can now also present quickly what is the uh, algorithm. So uh, but so essentially, it's a variation for QAOA, which is a quantum algorithm that defines a global wave function and then initializes the qubits with a Hadamard gate into a superposition, meaning that we define a function that um, has the state that we want to have. So I don't know, in portfolio, it's the lowest cost to buy the stocks, and also that yield or the lowest risk, but it yields the biggest profit. So that would be a cost function for a stock portfolio. And we initialize the qubits into a superposition where each qubit is equal, and then we find the lowest state using the cost function. So we apply the cost function, the global cost function, on the qubits, um, and and by progressively evolving the superposition, we eventually arrive at a solution where we see which qubits which represent the stocks are most likely or have the least global function. Um, what what is the problem of such approach is that it essentially just uh, maps what we know from the cost function onto the qubits, and then we can measure the qubits. But the quantum states are not somehow, they are not exploited enough. So the novel approach is initializing the qubits in superposition, um, and each qubit has its own wave function. So its own cost function, and then by forming the superposition, we see the current landscape of the market, and then we try to eliminate the qubits, the superposed qubits that do not share ideal state, which we define in another qubit. So that's basically the idea, and uh, I am I plan to implement it in like in this year or so. So that's my research. What's about. Thank you for attention.
Incredible, Oldrich. This was amazing to witness. I don't understand a lot of it because I'm from a different field. I'm just hosting the session. But I do understand that physics is such an intricate subject, right? And what you have been doing is usually taught at very high level. Dirac equation and everything is usually taught at like fourth year physics or master's level physics. So I was just wondering at what stage of your studies you are at.
I am now entering university, so I'm fourth year of high school.
You are in fourth year of your high school, so year 12.
Yes, year 12.
So
Yes.
so how are you able to grasp such high and complex subject and level of it? How did you reach there? Because this is exactly what is taught at fourth year physics level, especially like how you were utilizing this fine splitting principle, right? The first principle instead of using perturbation. How did you learn all these things? Because it's not something that is taught at high school at all, and it's extremely difficult to grasp. How did you get there?
Well, I think that the philosophy helped in the beginning as I developed my thinking intuitively, and yeah, had some ideas of how the particles might behave, and then I narrowed it down more and more with the particular equations and how those equations actually work. So it was iterative approach where I started with vague abstract sense of how the particles should behave, and then I navigate myself towards it. And I must admit that the technology is helping me in some sense. That, for instance, when I see an equation, I can ask ChatGPT or something to explain what's happening there. So that's the first thing, and the second thing is that I can. Validate if my current understanding is correct or if it needs some clarification. And when it's correctly prompted, then it gives somehow reasonable answers. Of course, then I also validate with professors and people, because that's uh, most important in the end.
Mm. Yeah. Um, Exceptional work, Ulrich. This is nothing short of exceptional and commendable. And with that, I'll open the floor for any questions there might be. Um, so we'll wait and see for 2, 3 minutes if there are any questions, and then we'll move to the next speaker. But your presentation was commendable, and meanwhile we wait, do you want to share anything else? How was your experience learning all this? And how did you reach this level? Have you been studying physics from a very young age, or did you just recently start diving deep into the subject? Can you share about your journey?
Yeah, I started learning more about physics like a year ago, or maybe half a year ago, 1.5 years ago. Um, and I started just from the popular science videos, explaining the topics, and that got me hooked into the subject. Um, and then when I entered the internship at Charles University, I started to focus on it more professionally, meaning to not just understand it on the popular culture level, but actually understand what is happening there in the equations. So that was my process, and of course because I was in the last year of high school, so I took physics as the final exam, so that also helped me to get more. Um, and then last thing that was really influential was AP Calculus BC, which um,
Okay.
yeah, it was hard, but it was very much rewarding, I'd say.
Amazing. Thank you very much, Ulrich. It was a pleasure looking at your work, and it was an honor. Thank you very much for sharing all your findings and whatever you have learned in this journey. And with that, we are done with this presentation. I don't think we have any questions at the moment. And thank you very much for answering whatever questions I had and for sharing your work.
Okay, thank you. Bye.